let's give this a go. So, as I mentioned earlier, we have been, at least last week, starting the circular functions area of study. So I figure since it's just us for now, other people will join, but for now, let's get you up to date on more or less where we're up to. So
Yeah.
circular functions, what we are talking about here are the trig ratio sine, cos, and tan, and what they would look like as graphs on a xy axis. So kind of like how you're doing polynomials and you're drawing your shapes and curves on the axis, you can also draw the circular functions on that axis as well. Now, the thing here to understand is this idea of the unit circle, which is a circle that has a radius of 1, and it is centered at the origin of that xy axis.
Yeah.
All you need to know for now is that theta is the angle for which you're going around the unit circle, and the x and y coordinates that intersect on that spot are given by cos and sine respectively.
Yeah.
That's about it you'll need to know for now. That's the background information for this anyway. What we're moving on to now is the solving of circular functions. So this is where what you essentially have is circular function equals some value over some given domain. And what we're trying to do here is solve for all the possible angles around that unit circle that get us this particular value. Now I have the full 4-step procedure here. That'll be helpful for all possible questions like this, but we're going to have a look at a fairly basic example here. First step in all of these is that we're trying to rearrange the equation that we have into what's referred to as an exact value expression. What that means is you want to have the circular function on one side, where that could be cos, sine, tan, any of those, and one of the unit circle exact values on the other side. Now, what I mean by unit circle exact values are these things here, the things on the outside, which are going to be root 3 on 2, root 2 on 2, or a half.
Okay.
These ones count as well, 1 and 0, and the negative 1, or so on and so forth. Basically any of those on this side.
Yeah.
Once we have that, we move on to step 2, which is if you have anything other than just x in those brackets, let's say it was cos 2x, then you would be going through this. But for now, we're just looking at a basic example, so we're going to go ahead and skip that bit.
Right.
Next up, we're going to try and find every spot on the unit circle that lines up with where cos is equal to root 2 on 2. This is where that background information is going to come into play. Understanding that cos is all the x coordinates is going to be helpful, because essentially all we're doing is looking for every spot on the unit circle where the x coordinate is equal to root 2 on 2. And that's going to occur at those highlighted spots there. Pi over 4 and 7 pi over 4. Those are the angles that correspond with that solution. And so that's what we write as our final answer. You'll notice that x was in this spot where the angle would go, which is why we're giving angles as our solution there.
Oh yeah. Okay.
Cool. Any questions about what's going on there so far, for anyone?
With the 7 pi over 4. Is that like? Is that is that different to pi over 4? Like, how does that differ?
Well, that is a good
just-
question, actually. Yeah, like how are they different? Because they do both give the exact same cosine value. So, are you familiar with like pi, these radians way of expressing degrees?
Not too familiar.
Not too familiar? That's fine. So let's pull that up just to get all on the same page. So you're probably mostly familiar with the fact that there's 360 degrees in a circle. There is an equivalence between radians and degrees, where radians is that thing that uses pi in it. Now, where that comes from is the unit circle, like I mentioned, and with the unit circle, because it has a radius of 1, and the circumference of any circle is given by 2 pi r, if r is 1, then what we can say is the full circumference of the unit circle would be 2 pi.
Yeah. Okay.
What radians is expressing the angle inside the circle in terms of the circumference that it covers. So for instance, if the angle is 2 pi, that means a full circle because the circumference was 2 pi. Whereas if it's pi, then that gets you half the circle.
Yeah.
So there's an equivalence equation that you can draw between the two of them that allows you to convert between them. So when you ask what's the difference between the pi r4 and 7 pi r4, it's purely just based on how far around the angle is with reference to the anti-clockwise direction.
Okay.
So pi r4 would be 45 degrees, for instance, and 7 pi r4 would be 315 degrees.
Yeah.
Now, as for the practical difference, both of them are actually the same for cos. They both give you root 2 on 2 as a value on the unit circle. But for sine, for instance, the y value, they are actually a bit different. Yes, this one's still root 2 on 2, but this one became negative.
Yeah, okay.
Cool. And this step 4 only applies if step 2 applied. So we're going to ignore that one. Next up, it won't always be the case that your equation is super easy to use off rip, right? Like this one here is not currently an exact value expression because we don't have the circular function on its own and an exact value on the other side. Technically we do, like 0 does count as an exact value on the unit circle, but the left-hand side is not what we need it to be. So we're just going to do a bit of simple rearranging. Plus the root 3, divide both sides by 2. That gets us the sine on its own, and the root 3 on 2 as the value that we're now looking for.
Yeah.
Again, no composite function. There's no 2x or whatever inside there, so we're just going to skip this for now. And we're just going to do the same thing that we did before, but this time for sine. Since sine is the y values, we're now going to look for all the spots on the unit circle where the y coordinate is root 3 on 2. And it's going to correspond to pi on 3 and 2 pi on 3 as our values.
Alright.
And that's it. Final answer. Again, step 4 is only a step 2 thing where applicable.
Okay.
Any questions so far?
No, not too many. No. Wait, go up a bit. Yeah, when it says 2 sine, does that mean like anything, or is that just like what you have to rearrange? Like,
Yeah,
would that change the graph or?
Yeah, so as far as the graph goes, we'll definitely look at that more so next week, but the 2 multiplicative on the sine is going to change the graph. It's a dilation factor. You would have looked at quadratics where you have like 2x squared, 3x squared, that sort of thing. You know how they stretch it in a certain way.
Yeah.
It'll also stretch the circular function as well. Yeah.
Yeah, alright.
And just like quadratics, if you had like a plus or minus at the end of it, that would be a vertical translation. Exact same thing here. This will be shifted down by root 3 on root 3.
Alright.
And so yeah, when we're graphing this, we would notice that those would come into play when we're actually sketching out the key features of it.
Yeah.
Cool. Now, so far I haven't really touched on what the domain has to do with things. I was just giving a default of 0 to 2 pi because that's the most convenient domain for us to have. It is not the only domain that you could have. It could be pretty much anything, but usually they'll either give a whole number, an integer number of revolutions around the unit circle, or they'll even get you to go in the backwards direction by starting to put negative values in the domain as well.
Okay.
So 0 to 2 pi just means that you're starting on the rightmost part on the unit circle and going in an anti-clockwise direction until you reach where you started.
Okay.
Negative values just mean going in the opposite direction instead.
Oh yeah.
That's the only difference there. In fact, if I show you a comparative unit circle to compare against, this is the equivalent negative version of the unit circle. So if we compare here, it goes pi on 6, pi on 4, pi on 3 in that direction. This one is negative pi on 6, negative pi on 4, negative pi over 3 in the other direction.
Yeah, okay.
So with that in mind, when we have a domain that is split, or even just anyone that goes negative, you essentially want to split this in 2 parts. One for a positive cycle and one for a negative cycle.
Okay.
So to keep it simple, I've just made the circular function really simple. No rearranging, no substitution. It's just where does sine equal 0. If we're just focused on the positive half of this, we would set our domain to be from 0 to pi. So in other words, that would be just the top half, the top semicircle of this.
Yeah, okay.
And all we're going to do is, because it's sine, we're going to look for where are all the y coordinates that equal 0. That's going to be that spot there and that spot there, corresponding to pi and 0.
Yeah.
We're now happy with that. We now go with the other half, the negative half of our domain, which means we're now looking at the bottom bit and we're going to be writing the equivalent negative versions of these angles. So we've already hit 0, we don't have to say it twice, but, and even though we've hit this spot, because this bottom semicircle hits it again in the opposite direction, we now call that negative pi rather than just pi. Because coming at it from the opposite direction, we'll notice that it all eventually leads up to now negative pi on that spot.
Okay.
And so all we do is list out all the ones that we just found, and that becomes our solution set.
Okay.
So you can extend this to whatever domain you get given. If it was, for instance, negative 2 pi to 2 pi, then you would do a positive part, which was the full unit circle, and a negative part, which was the full unit circle, but in the opposite direction. And you'll have access to the negative unit circle and the positive version of it, so whether you get negative or positive, you can use those as reference. Worth pointing out for those who aren't aware just yet, this unfortunately does not go on your formula sheet, and you will need this for tech free. So it's one of those things where you do have to have this memorized. I highly recommend looking at the previous lesson on this where I talk about memorization strategies for this, and giving that a browse, because memorizing the full unit circle exactly as written here, that's a lot of terms. Not great. And so I've essentially digested it in a way where you really only have to focus on this top quadrant. Now, I'm not going to get into that today. There's a recording for that already. So give that part a watch. It's only last week's video. And if it's still a bit of a challenge how to memorize this thing, anyone just let me know via Google form or even just direct message me for a refresher and we'll be able to give that a go. So you will need to have this memorized. Typically what it'll look like for a memorization strategy will just be copying it down like once a day or so. It'll only take a couple of minutes if you're using a reference and just copying down exactly what you see. But that's better than nothing. So unfortunately it is something we have to memorize. So getting onto it sooner rather than later, good idea. Okay, now we move on to one of the more complicated versions of solving circular functions, and that's going to be what happens if there's not just x inside our circular function. I've made this one probably more complicated than you'll get. Usually you have either a dilation factor or a translation factor, not both at the same time. But if you can handle both, then you'll definitely be able to handle one or the other. Step one, again, rearrange to get our exact value expression. So in this case, it's cos minus something equals 0. So let's go ahead and get rid of that minus a half. So we get just the circular function on the left and the exact value on the unit circle on the right. From there, we're finally going to figure out what step 2 does. Step 2 says we're going to apply a substitution to the function and the domain if we have a composite function. So as I said before, composite function just means anything other than x inside the brackets. The substitution that we apply is whatever's in the brackets. So if 2 bracket x plus pi over 4 is what's in the brackets, that's what we're going to do our substitution as. I'm going to use u, you use whatever letter you want, that's fine. We're doing this for simplicity. We're trying to bring it down to something that's a lot more similar and simpler to this, because all we were doing here was looking on the unit circle and then just saying what it was. It was fairly straightforward as long as you understood what you were looking for. When it's like this and you've got dilation factors and translation factors, you've got to look at where it is but also offset it in a certain way. Bit tough. So better to do this substitution approach. Now what that means is if we're replacing everything in the brackets with just the letter u, well, that's exactly what we do. Now it's just cos u equals a half. The other part of that, unfortunately, is that because the domain is in terms of x, and we're now using u, we now have to get the domain that we're using in terms of u as well. The way that works is we have an equation that literally says u is equal to this thing in terms of x. So we just grab these x values, plug them into our u equation to convert them into u values. So our lower bound of 0 is going to go in the x spot, and whatever comes out is going to be our new lower bound, in this case pi on 2. Our upper bound of 2 pi is going to go in the x spot, whatever comes out is going to be our new upper bound, in this case 9 pi on 2. This will be the toughest part of this kind of question, doing that substitution. Taking whatever's in the brackets, making that an equation, and then replacing the domain based on what comes out of that equation. So I'll pause here for now. Are there any questions about how that's worked? Cool. Okay. And if I go too fast at all, let me know in the chat or hop off mute. I'm happy to go back and talk about other things to build up the fundamentals. But for now, if we look at what we just created, this is now a lot simpler. I'm just looking for where is cos equal to a half, and this is the domain that I'm looking across. So cos equals a half, that's where all the x values are a half. That's going to be at pi over 3 and 5 pi over 3. Nice and easy. Now, that gets us our first two solutions, or at least our first two possible solutions. More so, I guess, the spots on the unit circle, where they are. But this domain is from pi over 2 to 9 pi on 2. So already, pi on 2 being here kind of cuts out the pi on 3 solution. So when all is said and done, we're not going to end up having that one. Furthermore, 9 pi over 2 is in fact bigger than 2 pi, which means we're going to have to do more than a single revolution around the unit circle. The way that works isn't too bad. Let's see, where did I write this down? Was it here? Actually, it might have been in evaluating. Let me pull that one up. The way this works isn't so bad. You essentially just keep counting around the unit circle. So the unit circle nominally goes from 0 to 2 pi, or in this case 6 pi over 3, right? Simplify down to 2 pi. But you can keep counting around additionally and keep just adding copies of whatever base angle you are adding around the unit circle. So if we're splitting it up into thirds, for instance, then you can keep counting around and just keep incrementing that numerator over and over again. That's how it works fundamentally. How you do it in practice is even easier than that. Because you know that these are fixed spots on the unit circle, there's only two spots where the x value is equal to a half, and we also know that 2 pi is a full revolution. Once we have our two spots on the unit circle, all we need to do is either add or subtract 2 pi to these angles to get the next revolution or the previous revolution. You would add to go forward, you would subtract to go backwards, because 2 pi is a full revolution itself. So by adding 2 pi to this, you say, okay, I'm currently at pi over 3, and I'm going to go all the way back around, back to where I started. And you just keep doing that until you get bigger than your domain, or smaller than your domain, depending on which way you're going. That's as simple as it is. So in two parts, part 1, you find the two spots on the unit circle. Part 2, you add or subtract 2 pi a number of times until you exceed both sides of your domain. In this case, it's going to take us 2 additional revolutions here. So we've got pi over 3 and 5 pi over 3, which we're adding our 2 pi to. And then we grab those ones again, add another 2 pi. And we'll do that until, well, in this case, it took us to 17 pi on 3, which finally is going to be bigger than our upper bound. It can get a bit challenging figuring out, hey, how exactly is this one bigger than that one? Or maybe this one's bigger than that one. What you can do is convert them to the same denominator, right? Because directly comparing a division of 3 to a division of 2, kind of challenging. You can do it by roughly estimating what the fractions are, but to be certain, what you might want to do is convert them to the same denominator. And that's just some fraction math, right? Cross multiplication. So you'd multiply this one by 3, this one by 2. That'll get everything to the same denominator. That way they're more directly comparable, which one's bigger than the other. In this case, it comes out to be the case that this one's too big and this one's too small. Right, this one's less than our lower bound of pi over 2. This one's greater than our upper bound of 9 pi on 2. So we're just going to knock them off from the list. And that gets us our solution set. There's a bit more to it than that, which we'll go into, but I'll just pause for now to see if there's any questions so far. All we've done is find our two solutions on the unit circle, add or subtract 2 pi repeatedly until we've mapped out everything that would fit in that domain. Any questions up till now? Cool. Okay. Problem we have right now is that we've written everything in terms of u. But this question said solve for x. X is an element of 0 to 2 pi, not u. So all we have to do now is fix our substitution, put everything back where it belonged. We know from our substitution that u is the same as 2 bracket x plus pi over 4. So instead of saying u equals all these things, we now say 2x plus pi over 4 equals all those things. All we do from here is rearrange for x. And that can be a bit annoying depending on how many solutions you have, but because you're doing the same operation to all these terms at the same time, it tends not to be the worst thing. Like for instance, dividing everything by 2, that just gives everything a denominator of 6. Nice and easy. Subtracting pi over 4, on the other hand, that's a bit of a pain in the ass because now you have to convert these to a similar denominator. But it is one of the things you have to sort of get through, and they're usually not too bad about doing this. Every time the examiners come up, usually they don't really put these translation terms in there, they just stick with the dilation factors, and those are much easier to unwrap back to x. So lucky in that case. The SAC might be a bit more annoying because the SAC will be more specific and targeted for particular topics. But this is kind of like your worst case scenario, just having to do a bit more fraction math. And what you'll see is that all the solutions that we've labelled are now back in terms of x, and they all fit between 0 and 2 pi. Right? This one's really, really close to being on the border of 2 pi. And so this is kind of the reason why we're doing this substitution approach. It's very hard, or at least it takes more skill, in my opinion, to estimate or see ahead of time what the factors are doing to where the unit circle spots are, and being able to estimate the 23 pi over 12 exists, given that it's so close to the border. Whereas if you do it this way, it doesn't really matter what they've said. You can just replace it with something much simpler and then unwrap it at the end using math rather than trying to sort of guesstimate your way through. There's merits to both. As you get much more experience with it, you can just sort of estimate your way through things and get the required solutions, and it's faster, but this will work in any case. Any questions there? Cool. So that's probably the worst case you'll get in the SAC, unlikely in the exam. Exam ones tend to be more like this. These are a bit stranger in terms of how you're solving them. They still conform to our 4-step process, but we just got to think a little bit harder in that beginning part of it, which is trying to get our exact value expression, because that means we need the circular function on the left and the exact value on the right. Problem here is we've got 2 circular functions, and there's no, well, maybe there's some really, really strange way via trig identities to get this into one trig thing, but I doubt it. And so we're left with the idea of, well, okay, how exactly are we going to get one circular function over on this left-hand side and exact value on the other? This is where we can use factorization to actually solve it. What we'll notice is that there is a common factor of cos in both of these terms. This is cos squared, this is regular cos. So there's 2 copies of cos here, 1 copy of cos here. You can factorize one of those out. That's going to get you this. How does that get us with one circular function on the left and an exact value on the right? Well, then we move into null factor law, which states that when you have a product of 2 terms equaling 0, either this one equals 0 or this one equals 0. We did this all the way back in quadratics, but the same idea applies to any terms that are multiplied together to equal 0. So that gets us two separate equations, either cos equals 0, that's this one, or cos plus 1 equals 0, that's this one. We have two separate things. This one, all we're going to do is subtract 1 to the other side to get our exact value expression. Now that we have our two equations, we just solve them individually. Where does cos equal 0? Well, that's going to be there and there. Where does cos plus 1 equal 0? Or in other words, where does cos equal -1? Well, that's just that one. Then we just summarize up the angles that we got for that. So all the main effort is going to be in identifying that you have a common factor that you can take out. The other leading indicator here is that it equals 0. Pretty much a lot of things that equal 0, you might want to consider a possibility of null factor law via factorization. You get taught a lot of that in your polynomials and your quadratics. So where possible, see if you can spot any common factors, because then you can use this kind of approach to solve the question. Any questions on that one? I think we've only got one more left, which is that we can also, in a similar context, try to convert down to one circular function. You can convert, I'll say most equations that have both a sine and a cos in them. You can actually, by some manner of math, convert the whole thing down into one circular function, tan x. And the way that works is, tan by definition is the ratio, the division of sine and cos. So if you can rearrange your equation in such a way where you can have sine divided by cos, you can rewrite that as tan, because that's what tan is by definition. So that's the approach that we've used here. We start by trying to get our exact value expression. In this case, the algebra is kind of whatever order you want to do things in. I've decided to move the cos over first and then divide. You can divide first and then move over. It doesn't really matter what order you do it in. The main thing you're looking to do here is identifying that you have sine and cos, and so any opportunity you have to divide sine by cos, you should take it. In doing so, the coses will cancel down to just 1 because you're dividing by itself. Anything divided by itself is just 1. And the sine divided by cos goes to tan. Whatever's in the brackets maintains. So it's going to get us √3 tan equals -1. We now have one circular function, which we can now rearrange for and solve, just like we've done before. Tan is a bit of a special case. If we have a look at our unit circle that everyone gets taught, it only has x and y coordinates on it. X for cos, y for sine. Where does tan come from? We looked at this last week, but just as a refresher, because tan is the ratio, the division of sine and cos, one way to think about it is it's just the y divided by the x. So for instance, if you did √3 on 2 divided by 1/2, what you would expect is √3. You would get that value for that spot. I've given you a full unit circle to reference for tan as well. Most schools won't do that, I don't think. My school certainly didn't. So this is one way that you can practice your tan stuff, just by using this unit circle. The other way is to memorize via the division idea. The final way that I can think about is, as far as how you memorize what's on this unit circle without referring to it, you can think of tan as the gradient of your line. Because gradient is essentially rise over run, y divided by x, and sine is supposed to be y and cos is supposed to be x, well, if we're doing sine divided by cos equals tan, and rise over run is gradient, that means that tan is effectively gradient. So when it comes to memorizing the order of this unit circle, you'll see that as the lines get steeper, the angles get larger, the values climb, right? √3 on 3 is less than 1, but 1 is less than √3, all the way up until you get perfectly vertical, which any vertical line has an undefined gradient. And you'll see again on this side, right, the angles, yes, they are getting shallower, but because the lines are going downwards, they're negative, right? Negative gradient. Any line that goes in a downward to the right direction is considered negative gradient. But okay, that's a little bit of a quick refresher on tan. The idea is still the exact same. If you have tan equals -1 on root 3, you're just looking on your unit circle, where is -1 on root 3? And that's going to be this spot. You'll notice it says -√3 on 3. The difference between the two is whether or not you've rationalized the denominator. This is something you learn back in like year 8, I think, year 9, where what they try to do is get this denominator as a rational number. In fact, I think I didn't really show it here, but there's a way to convert between -1 on root 3 to -√3 on 3. Where is it? Those are the same number. It just ends up being a matter of multiplying the top and bottom of your fraction by root 3, whatever the denominator is, because it'll cancel out the bottom bit and add the root on the top. Anyway, that's going to correspond to these spots on the unit circle. I've still got the sine and cos 1 there for some reason, but what you're looking for specifically is going to be the angles 5 pi on 6 and 11 pi on 6, because they'll correspond with that. This one also had a bit of a substitution thing going on a bigger domain. We've kind of already looked at that, so I kind of glossed over it. Because it was 2x, we were doing a substitution, right? Tan 2x equals all this, so replace with u and fix up the domain, which is why we have more than just the first revolution. And all we do at the end, divide everything through. That's about it for all the key examples on the solving of circular functions. Do we have any questions there? We'll get into some practice for sure, but if there's anything I should clarify before that, let me know. Alrighty, let's give it a crack then. So, what we've got going on. In fact, what I'll do is I'll do a copy as a screenshot of the tan and sine cos unit circles in the chat, so you guys can reference that, because you'll definitely need to if you don't already have all this stuff memorized. Okay, those are in the main chat now. Cool. Let me know if you have any trouble getting a copy. In the meantime, let's give one of these a go. Let's start with one that takes a little bit more effort than just immediately getting it. Let's go with this. So I'm going to do 4b here, and I'm going to start writing that up in the handwritten note bit. Okay, so we're going to have root 2 sine x is equal to, oh sorry, plus 1 is equal to 0. Plus 1 equals 0. Alrighty. I've got that one written up, so what I'll do now is for the screen share, I'll have up the approach that we use, the 4-step procedure. So you can use that as reference should you wish. Actually, what are we doing here? We're doing 0 to 2 pi. Okay. X element 0 to pi. Alrighty, what shall we do? How do we start this one off? Alright, I'll give a hint. First up, we've got to get our exact value expression, which means we want to get the circular function on its own, essentially. If I want to get the circular function on its own, what might I be doing? Put 1 to the other side, perfect. Yeah, we've got a plus 1, so let's subtract 1. Root 2 sine x equals minus 1. Is this the right? Hang on. root 2 sine x plus. That feels like a misprint. I think that's supposed to be a plus 2. Because I'm not going to find a... I picked the one thing in here that doesn't actually work out too well. Because we're going to have to divide this by root 2 and then it's just not going to... Oh wait, no, sorry. I'm being wrong here. Yeah, whoops, never mind. Yeah, so I kind of gave that one away. We're going to have to divide both sides by root 2 here, because again, we're going to try and get our circular function on its own. Sine x equals negative 1 on root 2. Now, this even sort of caught me off guard initially, because I was like, hang on a minute. We got root 3 on 2, root 2 on 2 and a half, none of which this is, at least not immediately. There is a way to convert, rationalize this denominator. Anyone want to remind me how we can do that? Rewriting negative 1 on root 2 as something slightly different. That's right. So as a quick refresher on rationalizing the denominator, we only ever look at the basic example of rationalizing the denominator, which basically just means look at whatever your denominator is and multiply the top and bottom of the fraction by that number. So in this case it's root 2, so we're going to multiply top and bottom by root 2. When all is said and done, that's going to get us negative root 2 on top, and root 2 times root 2, which is just 2. If we now look at our unit circle, we'll see, ah yes, root 2 on 2 is one of the values that we can now have a look at. Which is what we move on to now. We've got the circular function on its own, there's no substitution required. We now need to look on our unit circle and figure out where are all the angles within 0 to 2 pi, one revolution of the unit circle, where are all the angles that get us negative root 2 on 2 for sine. I've got that up on the screen share. You've also got a copy in the chat as well, should you wish. So as a refresher, sine, if we're solving for where sine equals negative root 2 on 2, we're looking for where the y coordinates are root 2 on 2, or specifically negative root 2 on 2. So like, this is your x coordinate, this is your y coordinate. So looking all over the unit circle, where do we have y coordinates? What angles are associated with y equals? Yeah, Nihal? With. You've come off mute, but I'm not actually hearing anything right now. Right. In fact, I'm actually hearing my own audio come back sometimes.
Would it be at 5 pi over 4 or 7 pi over 4?
5 pi over 4, 7 pi over 4? Yeah, those are going to be the spots there. So that's going to correspond with that negative y coordinate there, and this negative y coordinate here that I've highlighted on the screen share. And so yeah, we get 5 pi over 4 and 7 pi over 4 for those. X equals 5 pi over 4, 7 pi over 4. Yeah, that's pretty much it. 0 to 2 pi means 1 revolution, and as a bit of a pro tip, you're pretty much only ever going to have a maximum of 2 possible solutions any given revolution of the unit circle. At least when you're looking at it initially, after any substitutions have been done. Obviously, if you have dilation factors or whatever, you can cram more solutions in the same 0 to 2 pi domain. We saw that earlier. But as far as us identifying what the base angles are for them, you're only going to have a max of 2 possible solutions for any given cycle around the unit circle. That's it. So a little bit more complicated than just solve circular function equals value. We have to do a bit of rearranging first. Next up, we'll have one that has a split domain. So let's go ahead and do that. Let's go with cos equals -1/2. Let's try that one. Cos x equals -1/2. And we're doing that from -pi to pi. Minus pi, comma, pi. Okay, same idea. Not much has changed. Let me get the... Yep, that's the procedure. Cool. Cos equals -1/2 from -pi to pi. Already we have our exact value expression. Circular function cos is on its own, and one of the unit circle values is on the other side. And that's a simple one. There's just x in the brackets, so we don't have to do step 2. Step 3, where on the unit circle do we get cos equals -1/2? If it's easier initially, you can ignore the domain entirely and just focus on finding where on the unit circle do we get cos equals -1/2. Then from there we can be like, okay, what are they actually going to be?
You'd get -1/2 if you're at either 2 pi over 3, this causes the x coordinate, or 4 pi over 3.
Yeah, that's right.
Your domain's from pi to -pi.
Yeah, yeah.
So you would look at the bottom half.
Yeah, so -pi to pi, bottom half, yeah, I think you were saying it, yeah? Bottom half for...
Yeah, so would it be the bottom half that you're looking at? Or I'm not sure which one was it.
Yeah, so our domain being -pi to pi, what we'll end up doing is essentially splitting it in 2 parts. That's more or less how I think about having a split domain. You would first do whatever's between 0 and pi, which would be the top bit here, and give whatever that is, which will be the 2 pi and 3 spot, or the 120 degrees. And then the other part would be, if you're going to -pi, you would start at 0 and do the other portion here, just making sure to write this one in terms of its negative correspondent. Haley, I did notice you got the 240, which is good. All we're going to do from there is rewrite that in terms of the negative version because of that specific domain. But I did also ask, hey, just start by looking at where they are, and then we'll evaluate it afterwards. So we'll count that as a win. But yes, so to fix it up exactly as I mentioned, starting from 0 to pi, splitting it down the middle, you get this solution, 2 pi and 3, and then the opposite end, we now need to figure out what's the negative version of this, because that's from the 0 to -pi section. What is the negative version of this? There's a couple ways you can think about it. One would be to literally count in the opposite direction and get the negative versions of those angles. The other is a reflection idea. I'll go through both of them if no one gets it right now, but still have a think. Okay, so option 1, like I mentioned, is kind of just going around the opposite direction and counting that way. So normally we have pi over 6, pi over 4, pi over 3. Now we have -pi over 6, -pi over 4, -pi over 3, and so on. You're just physically reflecting wherever they were and going in the opposite direction. So if we wanted this spot, which was 4 pi over 3, now it's -2 pi over 3. That's one way of doing it, just counting around the opposite spot. So we would give negative 2 pi over 3 as our answer. The other way, I shouldn't have killed that document, it's going to need it now. The other way is to do a sort of reflection idea. And we're going to essentially borrow that from when we're doing our evaluating of negative angles. So just as a quick recap from last Mondays, if you had a negative angle inside your circular function, the first thing we did was say, okay, let's pretend it's not negative. Where is that? Well, if it's not negative 7 pi over 6, it's going to be the positive 7 pi over 6. Then from there, you physically just flip upwards or vertically from that spot, and then whatever's written there is the negative of your spot. It's the exact same idea over, where were we? Exact same idea for what we were doing, right? Which was we had this spot and this spot. We needed to rewrite this as its negative. Well, we just look upwards and then slap a negative sign on it. So if we flip vertically, we see, okay, 2 pi over 3 is that other spot, so that means this one must have therefore been negative 2 pi over 3. So that's another way of doing it without having to physically count around or memorize an entirely new unit circle. Any questions on those two approaches as to how you could be doing it? As for our answer, a nice and succinct way of saying it would be to say x is plus minus 2 pi on 3. That's a nice little thing about cos, as a bit of a pro tip. As you do a lot of these, what you'll notice is every cos solution is always in a vertical line. So cos being negative a half, the other solution will be in a vertical line away from it. Similar is true for sine. Sine is always horizontally opposed from each other. So y value of a half, y value of a half. This lines up with as we expect x and y values to make sense, right? Any x equals a number is always going to be a vertical line. Any y equals a number is always a horizontal line. Just a little pro tip. Sine will always be horizontally opposed, cos will always be vertically opposed. Okay, that's that. Let's see. I think there's a little bit left to go as far as lecture is concerned. We're getting a bit close to time. Maybe shouldn't be too much more to cover, so let's do that instead. So what we've been doing so far is solving circular functions over a particular domain. Right, we were told immediately what that domain was. What we're looking at now is what happens if we knock that domain off and just say solve for all x. Well, we've already seen a few examples of what happens when we have to do multiple revolutions around a unit circle. We simply find the two spots on the first cycle and then repeatedly add or subtract 2 pi until we get what we filled out our domain. If there's no limit to the domain, instead of just adding or subtracting a finite number of 2 pi's, we're going to add 2 pi n instead, where n is going to be a variable that will effectively stand in for the number of revolutions you're doing past the first one. It's not exactly what it is, but it's the way to think about it, the number of revolutions you're doing in addition. And this is what's referred to as the general solution, because you can plug in any value of n to essentially symbolize some number of revolutions to get whatever those solutions would be if you were to do that number of revolutions. It's a nice succinct way to give you infinite solutions for your infinite domain. And the rest of the procedure doesn't really change all that much. You still want your circular function on one side, the exact value on the other. You still want to do a substitution if it's getting more complicated in the brackets, and you still want to figure out where's my two spots on the unit circle for this solution. So in this case, it's sine equals negative root 3 on 2. That's here and here. Awesome. From there, we found our first two solutions on the unit circle. All we're going to do is plus that 2 pi n on both of those solutions, and that's it. Final answer. I've made it a bit more fancy by putting a little constraint on n, calling it an integer. You don't have to do that, they know what you mean when you do 2 pi n. In fact, I think some textbooks do like 2 pi k. It's just a little like out of concern for being misunderstood, you can put a little definition in there so that they understand this is your variable that you're using to iterate around the unit circle. No one should screw that up. No assessor should look at that and think otherwise, but just in case, you might be able to put that in there instead. And that's it. So if we imagine n being 0, that would cancel out each of those terms, and you would just get the first revolution worth of solutions. If n was 1, it would be the same as if you had just added 2 pi to your solutions, thus getting the second set of solutions. If n was negative 1, you'd be subtracting 2 pi. That would be getting the previous set of solutions. So in this way, we have one statement that encompasses all possible solutions of the unit circle. As for what we had to do, all we did was slightly modify step 3. So it's very much the same idea. Any questions on that example so far? Okay. What we're going to cover now is a few nuances where you can further simplify things for cos and tan. You don't have to further simplify things, it's just nicer if you do, and you might get marked you might get scaled more favorably if you give a better final answer. So, what does that look like? One thing for cos, as I mentioned, is that all cos solutions appear on a vertical line from each other. And we saw a bit of an example of this before. We had both the positive and negative version of 2 pi on 3. This is true for any vertical line here, where you can essentially only really focus on the positive solution that you have. So in this case, you have 5 pi on 6 and 7 pi over 6. Or I guess more accurately, you would pick the smaller of the two solutions, since both of these are technically positive. You essentially just pick the smaller of the two solutions, and rather than put plus 2 pi n on both of those things, kill one of them, and then just put a plus minus on the first. Because this spot, 5 pi over 6 and 7 pi over 6, this 7 pi over 6 is the same thing as negative 5 pi on 6. So a more succinct way is to just say it's both plus and minus 5 pi on 6, and then just put 2 pi n on that. It's just a bit more succinct. That's it. You don't have to do this, it's just something you might eventually do as you just get better at doing it anyway. You can absolutely just follow the exact same idea every single time and get the mark. This is just to write less down. Cool enough with that? Unfortunately, there's no real way to do that for sine. It's not as easy to draw a parallel between the horizontal aspect here. Cos it's easier because the way unit circles are represented as far as angles go, any incremental change in your angle counterclockwise is the same as if you were to go clockwise, and because you're going the same rough distance either side of 0, you're able to make use of that. Whereas here, the horizontal distances, they're a little bit, it's harder to condense that down. Tan also has one. So we have our tan solutions here and here. What we'll notice about tan is that any set of tan solutions appear on a diagonal between each other. So if you have the first quadrant pi over 3 solution, you'll have the third quadrant pi over 3 solution. So in this case we've got pi over 3 and 4 pi over 3. If we had 3 pi over 4, the other tan solution would be over here at 7 pi over 4. They're always off a diagonal on each other. And so because they're off a diagonal on each other, what you can do is, instead of having two solutions and then adding 2 pi n on both of those, so looping 2 pi's here, looping 2 pi's here, any diagonal distance between them is going to be a distance of pi, because that's half a circle, right? If you imagine drawing your half circle line via this diagonal, you'd have half on this side, half on that side. That is a total angle of pi to get from one to the other. So, kind of like with cos, we're just going to kill the bigger one and just add pi n instead of 2 pi n. So rather than having to do a full revolution from one spot, we do a half revolution rather than having to do full revolutions from 2 spot, we do half revolutions from 1 spot. So in other words, rather than going pi over 3, add 2 pi to get to here again, you can go from pi over 3, add pi to get to here, add pi to get back to here. Add pi, you now hit them in a more succinct way than if you had just added 2 pi n to both spots on that. So the most succinct way to go about it would be to kill the bigger solution and knock the 2 off of one of the pi n terms. Any questions there? Yeah, again, this is only a further simplification. This is a perfectly valid answer. The warning, so this is where probably most people are going to fail these kinds of questions, when you have anything other than just x in here. The procedure of how we do this has always been the same, right? We're still following the same 4 steps as before, just with a slight addition of the adding of 2 pi n. What matters is the order in which you do these things. As soon as you do your substitution to simplify things down and you get your first 2 spots on the unit circle, it is immediately after you get those 2 spots on the unit circle that you put your 2 pi n in. Then you rearrange to get the x back on its own. So you have 3x equals all these things and then dividing by 3 here. So in other words, your 2 pi n terms that you introduce need to be impacted by whatever's on this left hand side here, whether it's a dilation factor or a subtraction, a plus, whatever. It has to be impacted by it. So put your 2 pi n's in before rearranging to get the x back on its own. If you do it afterwards, you will get it wrong, because putting it in afterwards, you are essentially shifting the location of your spot on the unit circle, but not accounting for the fact that there are dilation factors involved. So do this first, then divide. That's the only warning to give. So long as you follow the steps in the exact order that I prescribed it, you'll be fine. It's only when you get into like the sack, under sack pressure, that you'll be like, oh shit, hang on, what order do I do this in? So practice that a lot. That's pretty much it. So general solution, not that much different, just one thing that's a bit of a catch for some people. And I say that because like I know I screwed this up at some point when I was doing my studies. So if I can make the mistake and have you guys not make the mistake, then that'd be great. The last little bit on here is on how we solve circular function inequalities. Now, I have a whole thing about how we can do this in a tech-free way. I don't think it's super relevant to watch in a tech-free way, because any circular function inequality thing outside of the textbook has always been a CAS question. It's always been in the extended response little bit, where it's like, hey, find where all the like wave heights are greater than something. Like, I'll see if I can find one. Yeah, it's like a boat can only cross the harbour when the tide is at least 2.5 meters above mean. This doesn't necessarily read like it, but this is referred to as a circular function inequality. It's not equal to 2.5 meters, it's at least. So greater than or equal to 2.5. How we handle that, I'll pretty much only show the CAS way because it's only what you'll need. How we handle that, more or less, is best done by just graphing the circular function. So what you do is you graph your circular function, and from there, depending on what the inequality is, will determine how you handle it from here. If we just assume a very basic where is cos greater than or equal to 0, whatever the number is that they've written there becomes your horizontal line that you're referencing. So cos being greater than or equal to 0 just means I want to know what's above, because it's greater than, what's above the horizontal line y equals 0. So, in other words, what domain of our circular function has the graph above y equals 0? And that's going to be from 0 to x equals 3, and from x equals 9 to x equals 12. You can cas solve these intercepts and find them. If I wanted to say, where is it less than or equal to 0, I'd be looking at this domain instead, and then giving that as my solution. If the line instead was here, I would want to be looking for, let's say we wanted to be above this blue horizontal line that I've kind of drawn. I'd be wanting to give this little bit of domain here, whatever that section is horizontally, and whatever this bit was horizontally. That's all we're ever doing. We're using the number that they're giving us as our horizontal line. If it's greater than, we're looking above. If it's less than, we're looking below. That's all you really need to know. And if you care a lot about like doing the tech freeway, I've got a full guide on it here. It's just, I don't think ever really come up. So, not super important, but there in case you need it. Alright, that's about it for time there. Do we have any final questions or concerns? Happy to stick around for a little bit longer to clarify anything. If not, oh yeah, go ahead.
I just want to know what's the best way to remember the units on the unit circle, or do you think we wouldn't really need to remember it?
Well, you'll definitely have to memorize the unit circle. That's something that'll come up in your tech free always. And you do not get this on your formula sheet. You don't get the sine cos one, you don't get the tan one. So, as for memorizing it, I mentioned earlier that there's a way to pretty much only focus on this first quadrant, and everything else is effectively some kind of reflection from there. To give you an idea what that looks like, if you just sort of look at these coordinates of root 3 on 2, a half, root 2 on 2, root 2 on 2, a half, root 3 on 2, if you look at any horizontal or vertical reflection of any of these given coordinates, you'll see that they're basically the exact same thing, with the exception of whether they're plus or minus. Do you see what I mean by that?
Yeah.
Now, the way you figure out whether it's plus or minus is based on your xy axis.
Yeah.
So, positive x's are left, negative x's are right, positive y's are up, negative y's are down. So being in this first quadrant, it makes a lot more sense why the x and y's are both positives, right? It's the top right part of your xy axis. From there, this is the left-hand side, so x's are negative, but it's up, so the y's are positive. So on and so forth for those. So you don't need to know any of these. All you really need to know is this bit, and then flip around there.
Yeah, right.
Sound good?
Thank you.
Yeah. Now that's just the coordinates bit, right? As far as the angles go, the way to think about that one is thinking about them in terms of fractions of a semicircle. Now I say fractions of a semicircle because they're all pi divided by something rather than 2 pi divided by something. 2 pi would be a full circle, pi would be a half circle. So as long as you know pi over 6, pi over 4, and pi over 3 are the base angles that you need to know, pi over 6 is just splitting this up into 6 parts. So pi over 6, 2 pi over 6, 3 pi over 6, 4, 5, 6. And you just count around.
Yeah.
Same thing with the pi over 4. So technically the only two base angles are really pi over 6 and pi over 4, because the others simplify into these anyway. But yeah, that's the simplest, bare bones way of getting it. Pi over 6, pi over 4, and count around, and then memorize these coordinates, and then just flip them around.
Okay.
Sound good? Cool. And I have this detailed in the doc as well, as a guide, and I've also verbalized this as well in a previous lecture if you want to watch the recording on that.
Alrighty. Thank you.
No worries. Take care. Any other questions? If not, I'll let you guys enjoy the rest of your day. No worries. Alrighty, we got 3 people looking for questions, or are we all just AFK?
No, I just wanted to ask a bit about integration.
A bit of integration? Yeah, sure. What's up?
How much time did you have?
A couple minutes.
Let me see if I can put it. Sorry, just one sec.
No, you're good. Yeah.
Yeah, it was from the 3-4 textbook, the 11K.
11K 3-4 textbook. Okay. That 11K. Is that average value?
It's fundamental theorem of calculus.
Oh, does that even have questions?
No, I just wasn't. Yeah, it was that page. I just didn't understand it.
Yeah, that's
The
nothing.
first page, like where it said 11K.
To be fair, like I don't even know if I've read this for a while. From just a brief glance, what are they doing? They're proving. I kind of talked about this before, actually, which was a bit about like why the definite integral of something gives you area under curve. That's what they're getting at there with a lot more math terms.
Yeah.
I've got the simpler version of that in my notes, which was essentially saying, okay, imagine like, I'll go through it now. Fundamentals. Did I do it here? Yeah, okay. So I was kind of taking it from the premise of like imagining your rectangle rule thing where you use smaller and smaller rectangles and gets you better and better approximations of the area. So if you take it to the natural extreme where you say you're having like really, really tiny like incremental widths of your rectangles, dx, so the distance of x, then the area of each of the rectangles is going to be length by width, or in other words, your incremental area dA is going to be f of x dx, because f of x being the height, the y value of your rectangle, and dx being the width. Are we cool so far?
Yep.
Okay. From there, you can rearrange this. It's a bit weird, but it's kind of it's a bit of a math weirdness whether or not you can treat derivative as a fraction, but for the most part we're going to ignore that whole pure math perspective and just do this because it does work. We're going to divide both sides by dx, giving you your derivative equation. dA on dx equals f. From there, if we integrate a derivative, we should go back to the original. So what we'll find is if we integrate dA on dx, we get back to a, and we get the integral of f, which in other words is your capital F, right, your antiderivative. So in that way, when you antiderive a function, that gets you area under curve. Whatever that antiderivative is a area function.
Unfortunately went to my spam folder.
Okay.
Yep, that makes sense.
That's all they're saying here in more technically accurate terms. Like this is more accurate than what I've described, but hopefully mine's more understandable than what they've said.
Yeah. I just on the one more. This was a quick question.
Yeah.
Because obviously my next hack's like mostly on focus on integration. But should I just look through the summary notes you have for? That's underneath the calculus folder, right? Are those the ones?
Summary. I mean, yeah, the calculus chapter, the calculus module has the integration stuff in it. Yeah, it'll be like the second half of it.
Just give me a call, please.
Yeah. Okay. Cool.
Yeah, it's got the notes there. But as far as your practice, I think we talked about this earlier, which was doing the chapter reviews.
Chapter review. Yeah.
Yeah. So that'll be still the main focus, unless you've already done it. Which congratulations if you haven't.
No, I haven't even started to.
Yeah, that's fair.
But I'm probably just gonna work my way up. Like, I'll try and finish the MCQs first.
Yeah.
Because I'm not sure if I have all of the basic knowledge yet, and then make my way up to the solutions.
Yeah, exactly. So basically, starting MCQ sounds fine. If you find you're getting a lot of them wrong, go back to the actual chapter sections where they belong, and then grind out a few of those and refresh yourself on that, and then return back to it.
Yeah, cool. I'll have a look tonight and see if I'll submit any question on the form. If there's anything like
Yeah,
that.
easy. I'll leave it to it then.
Thanks, Chris. Have a good night.
Thank you. You too. You got a question for me?
Yeah. So I do the one glasses, but Ben's not taking the classes anymore, right?
Yeah, that's right. So we do have to organise that now. Sorry, I didn't follow that up. It's been a bit hectic trying to organise things from that. Yeah, so you're still interested in doing those one-on-ones?
Yeah.
Okay.
Yeah.
So we can. I'll reach out and see if we can get another tutor to start running those one-on-ones again. It was the wildest thing. I don't know if he said much about it, but like his full-time job started picking up, and so he was no longer having capacity there. What did you guys have a set day that you were doing it, or?
Wednesday.
It was mainly Wednesday. Cool. Okay.
Yeah.
So I'll keep that
Every
on.
other Wednesday.
Yeah, every other Wednesday. Cool. And you still want to more or less have that every other Wednesday idea?
Yeah. Yeah.
Cool. Okay. I'll keep that one in mind. I'll see if we have a tutor that has exactly that. If not, we might have to change a different day. Do you have any other availabilities?
On the evening on the weekends.
Yeah. Okay.
Yeah.
So basically anything that's not the group classes.
Yeah.
Yeah. Okay. Cool. I'll keep that in mind then. We should be fine. But yeah, I'll follow that up and we'll get that sorted. I can message you. Actually, I'll give How did we do it last time? Yeah, I'll get them to contact you. I think I got your number.
Maybe.
Yeah. Okay.
Yeah.
I'll have a look because Matthew definitely had your number, so I'll grab it off him at the very least and I'll organise something to happen. Okay.
Yeah.
Cool. Thanks for that.
Okay. Have a good day.
No worries. You too.